Hey gents, in this video we're going to work out how to work out the acceleration that are caused by forces at funny angles. And what do I mean by funny angles? Well, we're used to, up to now, dealing with situations where the forces are left, right, up or down. In a situation like this though, we have some forces that are sort of sticking out at weird angles there. Now, I've taken pains to draw this diagram so that it's sort of as close to as scale as possible. So notice that this 80 Newton line is roughly twice as long as this 40 Newton line. The 50 Newton line here, a little bit longer than the 40, not as long as the 80. Now that's important because the first method we're going to use to solve something like this is actually a pictorial method, right? So it's not quite as mathsy. The second method we use is a little bit mathsier. So the idea that we're going to do here is we're going to turn this diagram here into what we call a free body diagram. And a free body diagram abstracts away the object and just sort of turns it into a single dot. So we're going to start with that. Here's our single dot, right? And then what we want to do is just take each force and place it head to tail on this dot here. So we might start with that 50 Newton force. Here we go. There's our 50 Newton force. Then we're going to take this one here and pull that down over here. There's our 40 Newton force. And we can take care of that angle there as well. We can pop that in here. That's 30 degrees. And then lastly, we're going to take this 80 Newton big boy and put it on the end. So notice when I'm adding them up head to tail. So the start of the next vector comes from where the last vector ended. So we're going to take that 80 Newton one, and that's going to look something like that. Right. And I haven't been that careful with the length of my lines. If we want to be really careful, we'll do it the mathsy way in a moment. This is just to give us a sense of what's happening. Right. So the angle here, that angle in there is going to be 20 degrees. And notice that we started here with our vectors, we added them all together, and we ended up all the way over here. So our final vector is going to go from where we started to where we ended. And sort of with this pictorial method, all you're really looking for is roughly how long is this line? I don't know, it's about as long as the 50 Newton line to begin with, so maybe 50 Newtons long. And in what direction does it point? Well, it's more up than down, it's more right than left, so we would expect this object to accelerate in that direction at roughly, 50 Newton force on a 20 kilogram object at roughly 2 and a bit meters per second. So we would expect the acceleration to be sort of in that general direction at maybe 2.5 meters per second squared. Okay, that's one method. That doesn't get us a really exact solution though. That just sort of gives us a general sense of what's going on. We might want to know like the exact solution, the exact acceleration that we get out of this. In order to do that, we do a thing called resolving components. To resolve components, what we do is we take every vector which is not at a nice up, down, or a left and right, and we actually turn it into two vectors. One which points up and down, one which points left and right. So let me take the example of this 80 Newton force here. We can think of this 80 Newton force not as one force on a diagonal, but as two forces. One which goes horizontal, and one which goes vertical, which together add up to give us that 80 Newton force. And if you look carefully at that, what you have there is a right angle triangle with an angle of 20 degrees in here, a hypotenuse of 80 newtons. And so we can actually find out what the adjacent and what the opposite are. Do that in using the magic of video. I'm going to do that in about 3 seconds, but obviously you're going to get out your scientific calculators and work those out. As you can see, once we're done with that, we get that 80 times the cos of 20 degrees is 75 newtons, and 80 times the sine of 20 degrees is 27 newtons-ish. So what you're finding is, as you'd expect, this force is a lot more rightward than it is upward. We can do the same thing with this force over here, same idea. This sort of down and left force can be resolved into a downward force and a leftward force. And once again, we have a right angled triangle there. And I'm going to resolve those components again. This one's going to be 40 sine 30 degrees because it's opposite that angle. This one's going to be 40 cos 30 degrees because it's adjacent. Let's do that quickly. Okay, and we find that the leftward component of this is 20 newtons, and the downward component is 34.64 newtons. Right, now that we've got all of our forces resolved into our nice cardinal angles, left, right, up, down, we can add them up like we would normally. So we can say, what are all the upward and downward forces in the problem? We have 50 newtons up, 27.36 newtons up, and 34.64 newtons down. So the total up-down forces are equal to 50 plus 27 plus minus 34.64 newtons to give us a grand total of 42.72. That's pointing upwards because we have more upward forces than we do downwards. And what about our left and right forces? Well, they're going to be, this one here doesn't have any left and right component. This one here points 75.175 to the right. This one's 20 newtons to the left. So our total is going to be 55.18 newtons right. That one was up before. Right, so what should we expect our object to be doing? Well, it's going to be accelerating 2 and a bit meters per second to the right, and about 2 meters per second upwards. Now, if we wanted to know the total acceleration, we could use Pythagoras on these two to get the overall net, although it's usually more important to know the directional amounts than it is to know the overall magnitude.